Good morning, everyone.
Yeah, good morning. Good morning, everyone.
Welcome you, sir, again for today's session.
Thank you.
And all the participants, already you know about sir, and sir explained yesterday very briefly about he started from like classic computation to the quantum computing, towards the quantum computing and all. And we got lot of idea, lot of information about the quantum computing. Today, I will continue with some algorithms and all. Welcome you, sir, and over to you, sir.
Thank you. And good morning, everyone. So everyone is able to hear me and see my slides?
Yes, sir, we can see. Now I will make them.
Allow them to speak?
I will allow them. Yes, sir.
Okay. So good morning, everyone. So yesterday we have seen about this, how this quantum gates and qubit work. And today we are going to see some very important quantum algorithms which do some meaningful thing which is not possible on classical computers. So one of them is Grover's search algorithm. So what this, so before starting it, what is the importance of search we should first understand. So let's suppose we are having this kind of table. Okay, so where this personal data is available, person height, age, weight, and IQ are available. And let's suppose this data is not sorted at all. Okay, so if I want to find this Greg in this table, then what I have to do? Can anyone tell? If this data is not sorted and I want to look for Greg in this table, then what I have to do? Anyone, please?
So is it required to search each and every data or elements?
Yes. So we have what we have to do is we have to look for this column person, and we have to try for all names where this Greg matches. We will say, okay, this is the record which we are looking for. So this is the scenario when data is not sorted in any order. So this problem is like if data size is, let's suppose, capital N, that is let's suppose 2 to power n, then what is the complexity to search a name in this kind of table or database? Worst case, anyone, please?
Worst case is n, is that not?
Yes, n. So we have to look for every person's name in the table one by one sequentially. Okay. And what is the best case?
If it is first element.
Yeah, good. So if it is first element, then we are lucky. But generally, on an average, what happens? N by 2 element we have to search. So worst case it is n, best case it is 1. But on an average, if we look for sequentially, then it is order of n by 2. So that is basically order n only. So the complexity is order of the size of this table or database. If suppose n entries are there, then complexity is of order of n. Can we do better in classical scenario if let's suppose data is sorted?
It can be in binary manner. Binary search algorithm can be done.
Yes. So if data is sorted, then we can apply binary search. And how we search when data is sorted? Binary search idea? Sorry?
Sir, I don't get you.
Yeah, my question is, if this data is sorted, then how you will search?
That's what we have. Okay, binary search in the sense we first start until we go to the middle.
Okay.
If it is going to be before or after. So it
Yes.
depends from 0 to n by 2 would have come.
Okay.
So that's what either it could be this half or the remaining half will be searching.
So there was such log n steps will be there to
Yeah.
determine the element in sorted kind of thing. But sorting itself take what is the complexity of sorting?
There's some distraction. I don't really get you.
Yeah, just a second. Who is there? I think yeah. Yeah. So what I'm asking.
Some Nagashruti, please.
Yeah. Nagashruti, please mute yourself. Nagashruti, mute your mic.
Sir, I muted, sir. I muted.
So the question is, sorting also takes some effort. And what is that effort? If n elements are there and we want to sort them, then complexity of sorting is?
Log n, I remember. Yeah.
No. It's n log n.
N log n. Okay, sir. Yes,
Yeah.
sir.
So that is also more than this n. So,
yes, sir.
And if we are using this table frequently for searching the name, then we can sort it once. But let's suppose if sorted for name and I ask for this weight or some other field. So we cannot sort for all fields. This is the restriction, because we have to sort if for all the fields, if we'll sort, then it will take memory also. So generally, if you see, search is very important thing. And most of the time in practical scenario, what we do is whatever field we want to search frequently, we sort the data on that field. Here, if we see that, then we will sort on the name of the person. We sort the data once, and then we can search in log n time. But the condition is the data should be sorted. So let's suppose data is not sorted. Then, as you told, the complexity will be of order n. Is it clear?
Yes, sir.
Data is not sorted, then the complexity is of order n. So where else we will find searching? Let's suppose this kind of city map is there, and somebody wants to go from one place to other. Then let's suppose there are total n paths. Then what we have to do is, if we are not using any, we want to search the best path. Then in worst case, what will we have to do? We have to check all the n paths one by one.
Okay.
So if there is no sorting kind of or ordering is there, then it is order n. But in 1996, Love Grover, an Indian and IIT Delhi alumni, has proposed this algorithm, Grover search algorithm, and he showed that this kind of search can be done in order of square root n. So earlier it was order n, and he reduced this complexity from order n to square root of order n. So, and it is for unordered data we can search. So the idea is that let's suppose this capital N is basically small 2 to power small n. So we will keep this thing in mind. Whenever I am saying capital N, that is this, and that is equal to 2 to power n. Okay, and n will be the number of bits used to represent the data field. So how this algorithm work, and the criteria is that this algorithm work on a quantum computer, and if the data is inside the computer, then we can search in order of square root n time. How it works, we will see in the next slides.
So one small doubt, is it not relating to a relational RDBMS, relational database system? If that is the case, we'll have primary key, or we are going to just have a simple database without any primary key concept?
Yeah, so the second one, there is no primary kind of primary key of kind of concept. So whatever field, let's suppose some other field you want to search, then you can search. So there is no primary key kind of thing. You just simply say that there is a data table is there, and there are some fields and some values.
So it can be searched from any field, any element from any of these fields. Okay, sir.
Yes. So whatever the data field you want to search, you can apply this algorithm for all the fields again. So let's suppose this was the table. So it can do this kind of searching for all kind of fields. Maybe it is person name or height or this age. So using this, we can perform basically search on an unstructured data or unordered data in order of root n time. So the idea is that what is this capital N here? Capital N is basically the size of this database or number of entries in this data, or here this number of paths. And what we are assuming for our understanding that this capital N is basically small n number of bits are required to represent this n. Are you getting this? This is total path.
Yes, sir.
And small n is basically number of bits required to represent this capital N. Okay.
Yes, sir.
So this is the idea, and yeah. So algorithm is very simple. What we do is first we start with state zeros. So all qubits basically will be initialized with. So what we do is we will choose this number of qubits, small n number of qubits we will initialize with 0, and then we apply Hadamard. So yesterday we have seen if we apply this n Hadamard gates on this n qubits which are initialized to 0, then what it does, it will create equal superposition of all states possible with this n bits. So maybe it is starting with all zeros n time to all ones n time. So how many entries will be there? Basically 2 to power n amplitudes simultaneously will be existing in this superposition. Anyone have any doubt about this?
No, sir.
So basically the idea is that we are having 0 qubits initialized, then we apply Hadamard, then we will have all possible states of n bits with us. Then we apply this Grover operator, square root of capital N times. Basically capital N is basically 2 to power n. So we will apply this the Grover operator that we will see in following slides. So what we do here is we apply this Grover operator square root of capital N times. And after this operation, when we measure these qubits, this n qubits, we will get the desired, the item which we are looking for with high probability. More than 50%, we will get the desired searching item. So how it works, there are some assumption or some conditions are there that we will see in next slides. So if you see this algorithm in block diagram view, then it looks like this. So initially, this n qubits are initialized with 0 that I have already told. Then we apply Hadamard gate, and we use some one auxiliary qubit that is initialized with 1. So this is auxiliary qubit that is we used for implementation of our Grover operators. So this shaded block is representing this Grover operator, and then we apply in square root of 2 to power n times, and then we finally measure this n qubits. So when we measure, we will get with high probability the desired answer or the item which we are looking for. So this operator we will see in detail how they work and how. So initially, if you see here, all states are equal likely. Yesterday we have seen for single qubit, 2 qubit. So let's suppose if I apply this Hadamard for 1 qubit, then what we will get? We will get 0 plus 1 square upon square root 2. So basically on measuring it, equally we will get 0 or 1, 50% probability. If we are talking about 2 qubits, then there will be 4 choices. So at this stage, we are having equal likely of all possible 4 choices of 2 bits. So after this superposition, we are having all states are equally likely. Here, probability of getting all states is equally likely. But after application of this operator at this final measurement, what we will have? We will have high probability of the correct answer. So is this logic clear to you?
Yes, sir.
So let's look into detail of this phase inversion and inversion about mean operators, how they work and how they are implemented. So before going to detail, so what we do is time being you understand this search is basically if somehow we can represent our search logic in terms of some function, okay, some Boolean function. So this fx is our search logic, and this item x star which we are looking, okay. So whenever we are having this x star, the desired item which we are looking for, that will satisfy this function, other item will not satisfy. So the idea is that our whatever we are searching, we are having a Boolean function that is f, and what this function does is this f is satisfiable only when we supply the correct input x star. For rest x, it is 0. Okay, and in the oracle, what is happening is whenever we are applying this oracle operator, so just understand like this uf is basically a gate. What this gate does is whenever it is applied on some state x, it will change the sign of state x if fx is 1. So understand here what is it is doing is whenever this fx is 1, basically x star, then it will change the sign of the state, desired state, and for other it will remain same. So what is this phase inversion is doing basically? It is changing the phase of desired state, that is x star. So if we are searching for x star, then it will change the sign of that value. And what is this amplitude amplification? So if you see here, then this phase changing will not increase the probability, because whatever the phase plus or minus, the probability will same on measuring this values. So you understand? Whenever we calculate probability, that is basically amplitude mod square. So here amplitude is just changed, sign is changed. So sign changing will not will not increase the probability of desired state. So here just only sign is changed or the phase is changed. But the second operator, that is amplitude amplification, that is part of this Grover operator. What it does is it try to increase the probability of this desired state. How it does, we will see geometrically and with example also. So understand, this Grover operator is basically having two operators. One just changes the sign of the desired state, and other try to increase the amplitude of correct state. So initially all states are equally likely, and after one iteration of this Grover operator, it will increase the probability of desired state. So if we apply this operator square root of n time, then finally we will have more probability of getting x star on measurement, or other states will have less probability or will miss in the measurement. So this is the high level idea of the algorithm. So just this is the Grover operator which you have seen, and we are applying it square root of n time. And what is there to implement this Grover operator? So we see here, we are saying that it's oracle, that is changing the phase of desired state. So whenever this fx is 0, it will remain same. Whenever fx is 1, it will change the sign. So when fx is 1, when we are having the desired state in x, then only it will change the sign. And this is other operator that is basically doing the amplitude amplification. Okay. So, and it is implemented in this form. So now come to how this algorithm search. So basically idea is that we are having this kind of total n values are there, 2 to power small n. So these elements are there, and we are looking for one state x0. That is our solution. So when we apply this psi state as an input, so this is having equal probability of what is the initial state we are supplying here is equal superposition we are supplying to the Grover operator, and on measurement we are getting x0, the desired state, with high probability. So see here. So this is the circuit diagram. If we look for this Grover algorithm, so these things are clear to you, that we are just initializing the n bits with zeros and then applying the Hadamard, and then we are using another auxiliary qubit 1 and apply Hadamard over it. Then oracle operator, then this inversion about mean operator, and we do it several times and then we measure. So to draw the circuit for this algorithm, this diagram is useful. Now we will see how the steps are performed for n is equal to 4. So in that case, what is the small n for capital N is equal to 4? The small n is basically 2. So basically we will take 2 qubits here and initialize them with 0. Then we will apply Hadamard on them. Okay. So if we see here, in case of small n is equal to 2, what we will have after this Hadamard application on these 2 qubits initialized with 0, we will have all possible choices of 2 bits. Everyone remember this thing? Yesterday we have done lots of this kind of thing. On application of this 2 Hadamard, we will have equal superposition of all possible states. And what is the probability of getting 0, 1 here? If we measure this psi here, what is the probability of getting 0, 1?
1/4.
Yes. So for everyone it is same. Is it clear? For every state, if we see here, probability of getting them is equal, and that is 1/4 for all state. So initialization probability is equal, but what our goal is, after repeated iteration of order n time this Grover operator, we want to increase the desired answer. Let's suppose our desired answer is 1, 0. Then what we want to do in this process is we want to increase the amplitude and the probability of this 1 0 and simultaneously decrease the probability of others. So if we, let's suppose, after this iteration, here some, let's suppose 1 by, you can say, suppose this amplitude of this 3 state has decreased and amplitude of this state 1 0 has increased to 1. So this, if amplitude of this 1 0 is 1, then amplitude of this 3 state will be 0. On measurement, we will get 1 0 only. In ideal situation, if we perform this operator and measure, then amplitude will increase such that only this state will remain. That is our answer after application of this Grover operators. So this is the first step which we have seen. But at this stage, if you measure, then you can get any answer. So you cannot make out any meaningful information measuring here, because all are equal likely. So you cannot decide which one is correct. So for that, we apply this Grover operator. Next is this Grover operator, and how we implement it, we'll see here. Just a second. So let's suppose our x0, basically the solution, that is 1 0. Let's suppose we are looking for 1 0. And this search, then what will happen here? If we are looking for 1 0, then we should have this kind of operator. What it will do is, for x0, basically for state 1 0, it will change the sign, phase, and for others it will remain same. So if you see here how we implement it, we will see in the demonstration. Just time being, assume that this is the oracle function, and what it does is it changes the phase of desired state. Okay, and this is how it works. So after application of this oracle, what will happen here? The desired state, suppose, is that is basically that is 1 0. So we are looking for 1 0 in our answer. So after the application of this oracle, what will happen? Sign of this state will change. Basically, sign is basically phase. So they are in phase 0. It is in opposite phase. So that we can do using some quantum gates. Now what is happening? This is the part of algorithm. So what we do is, again we apply Hadamard gates, and it is part of that amplitude application operator. Okay, and what it does? Can anyone tell?
It changes the phase.
No. This first one is changing the phase.
Amplitude,
second one is,
sorry, sir. Amplitude.
Second one is ultimately it is doing phase also, but it is doing phase change for amplitude amplification.
Yes, sir.
So after application of this operator, we will have more amplitude for desired answer and less for others. And if we increase the amplitude, then it means the probability is also increasing. Is it clear?
Yes, sir.
So see here. So first step is done. Sign of this state is changed. Second step, we apply this Hadamard over these 2 qubits. So if you see, then what will be happening is, if we apply Hadamard over 0 0, then what we will get?
0 0.
No.
Sorry, sir.
We will get all possible 4 choices. That is,
yes,
like,
sir.
See here. What we did here is, initially these 2 qubits are initially 0 0, and then we apply Hadamard. So what we got?
All combinations of 0 0 0 1.
Yes. So this, on this 0 0, if we apply Hadamard, 2 Hadamards, then we will get all possible 4 like this.
Yes, sir. Yes, sir.
And on this 0 1 we apply, then we will get all possible, but with different signs.
Okay, sir.
So each one will produce 4 such states. So the total, basically there will be 16 such states with different phases. So everybody is getting me? What will happen here? So what is happening here is that after this state, if we apply Hadamard, then this one state will goes to 4 possible choices with different amplitudes and different phases. Similarly happen with this also, this also, this also. So there will be total 4 cross 4 states, combination of this only 0 0 0 1 1 0 and 1 1 only, but with different amplitudes and phases. So what will happen is, then when this, let's suppose this state comes with positive sign also, so then positive and negative will cancel out. So there will be total 16 states, and some of them are in opposite phase. Those will be cancelled out, and finally we will have this kind of state. See here, we will be left with these 4 states. And if you see the difference, then what is the difference happening here? This just all are same, but just these 2 phase are changes. It was plus minus, and it will become minus plus. Okay. Then what we are saying is change the phase of all states except 0, 0. Here. So we need to change the phase of every state except this 0, 0. So changing the phase, what it will do is it will change the phase of this. So it will minus 2 plus it will become plus 2 minus, it will become plus 2 minus. Is it clear?
Yes, sir.
Again, what we are saying is, again on this state, we are applying 2 Hadamard gates. So what will happen with this 0, 0? It will split into 4 states.
4 states.
Similarly, this will also split into 4 states. This will also. And then some state will cancel out and we will get this kind of state. So what is happening here is when we expand all of them on application of this Hadamard, we will left out with this 1, 0 only. All other state will be cancel out. So this cancelling is basically destructive interference, which have been told you in the first day sessions. So what is happening here is constructive and destructive interference happen. So for this 1, 0 state, constructive interference is happening and its amplitude is added. For other, the phase is different and there is destructive interference is happening, and those amplitude is reduced. So what is happening here is that due to this destructive and constructive interference between states, desired state amplitude is increased and other is reduced, and reduced in such a way that after one iteration only, this state is having one amplitude and other are vanished. So if we measure after this, then what we will have 1, 0 only with 100% probability. See here, since this is case of this here this capital N is 2, and for it is a special case that on iteration one iteration we are getting the answer. Why we are getting? Because the expression is the exact expression for this square root of capital N is basically pi by 4 square root n is the formula. The precise complexity is not exact, not square root n, it is pi by 4 into square root of n that we will see. So that turned out to be 1 only. So for one iteration, we are getting the correct answer. For n is equal to 8 also we will see. So before moving to other example, I just want to recap you and understand what is happening here. Initially, we initialize all the states with all possible choices. Okay. Then we apply the Grover operator. What application of this Grover operator does is it increases the amplitude of desired state and decreases the others. So for that, this constructive and destructive interference happens. And after square root of n application, but in our case, simple case, one iteration is sufficient for capital N is equal to 4. When we measure, we will get the desired answer with high probability. So I think you should be able to understand that these are this changing the phase of desired state here, change the phase. Second step, we apply this Hadamard. So on application of this Hadamard, we will have each state will goes to multiple stages, and then some phase difference is there. So some substates will cancel out and we will get this kind of state. Then we changes the phase of all states except 0, 0. Then we again apply Hadamard. So again, this constructive and destructive interference happen and we will get 1, 0 as our answer. So we will see how to implement those in actual quantum computer or quantum simulator. So today we will try to implement those on a different quantum simulator in the practical at the end of the session. So as we have already seen, yeah.
Sir, is this for all n, sir? If it is n is equal to 5 or n is equal to 8?
So what we try to do is, let's suppose if your capital N is 7, so then what we will do is we will keep this small n is equal to 3.
Okay.
Because 7 values cannot be represented by 2 bits.
Oh, yes, sir.
If you want to represent 7 values, then you should have more than 2. So basically, if you have 3 bits, then you can represent basically 8. But for 7 also it will work.
7 also it will work. Okay, sir.
Yeah. So sometimes you have to take 1 extra bit to represent the not extra. because that is the bare minimum requirement to represent 7. Let's suppose if you have,
okay, sir, will it converge in one iteration for every n bits?
no.
Not
It is
necessarily.
the special case for n is equal
N
to
equal to 4.
4.
Okay, sir.
One iteration, it is sufficient. Let's suppose if we go for capital N is equal to 8,
8.
then they will require 2 iteration at least.
Okay,
Okay.
sir.
If we measure after one iteration, then probability will not be that much that you will get with more than 50% probability. So after square root of an iteration, it is highly likely that you will get this state. So it is highly likely is basically more than 50% probability you will get this. So more than 50 is sufficient for our practical purposes.
Okay, sir. Thank you. Thank you.
So again, just recapping this block diagram, and we will go through some mathematical concrete example that will you will be able to understand better. So this is the block diagram, and what we are saying is that state by state, this at the first stage, let's suppose we are having this phi 1 state, and then how these states are progressing in this implementation, we will see here. So let's suppose if we are searching for 101, okay, and so basically it is a 3-bit kind of thing. So we will require 3 qubits, okay, and this 3 qubits will be represented by 30 qubits, okay. So initially what is happening, all 3 qubits are in 0 state. So basically we will having amplitude of this 0001, rest other states are not there. So I'm talking about this point. Is it clear? At this point all 3 qubits are in 0 state. So basically 000. So amplitude of that state is 1 and other states are not there. Is it clear?
Yes, sir.
Then we apply Hadamard to create equal superposition. Then what will happen? Yesterday we have seen if we apply on 3 qubit 000 3 Hadamard, then we will have all possible states with same amplitude. And what is that? That is 1 over square root of 8 or 1 over square root of 2 to the power 3. Because 3 qubits are required. So basically here it is capital N is basically 2 to the power 3. So if you see, then probability of getting each state is basically 1 by 8 mod square. This is amplitude. See, this 1 by square root is the amplitude of this 000 or all the state 110 is also 1 by root 8. So this is basically amplitude. And what is the probability? Can anyone? If at this stage I measure this 3 qubit, then what is the probability of getting 110?
Equal probability for all cases.
Yes. What is that value?
0.25.
No, make it like this. Square root of square of this thing, no?
Yes,
this
sir.
is the amplitude. Mod square of this. This is the amplitude of this state. So just mod square of it. That what that will be? 1 by 8.
8.
And 1 by 8 is 12.5.
Okay, sir.
So all are having same probability. That is basically 1 by 8. That is basically 12.5%.
12.5. Okay,
so if we measure here, then we are not getting this 101 with more probability. 101 is also having the same probability. So you cannot distinguish between wrong and right answer here. So now comes our Grover operator. Some distortion is happening. Okay. So okay, some formatting is misplaced formatting is happening here. So okay, so just to yeah, let's keep it here. So what is another operator that was changing the phase of desired state? So our desired state is basically 101. So after that, what will happen? Initially, all are having the same amplitude. That is basically 1 by root 8. After this phase inversion operator, the phase of this state will change. That will be minus. So earlier it was plus alpha 5. Now it will become minus alpha 5. So is it clear? So what is happening is just changing the sign of this amplitude. So amplitude is changed from plus to minus here. Okay. So now if we compute the average of this amplitude. So what is the average of amplitude here? These all 7 are positive value and 1 is negative. So how we can compute the average of amplitudes? So 7 time it is basically 1 by root 8, and 1 time it is negative. So if we solve this, and for average we have to divide by 8. So we are getting this amplitude, that is basically 3 by 4 square root 8. Is it clear? What we are computing here is mean of the amplitudes. So that is this one. Earlier what it was? Initially it was 1 by square root 8 only. So what we are doing is, in the second operator, we are inverting about the mean. And that is done by this minus v plus 2a, where a is our mean or average amplitude. So if we, for all the states which are not desired, this is 1 by root 8. So amplitude is, value of v is 1 by root 8. And if we compute this minus v plus 2a, then it will come to 1 by 2 square root of 8 for those states which are not desired. In case of desired, value of v is basically minus 1 by root 8. So if we put minus 1 by 8, or minus 1 by root 8, then it will positive, and this will the amplitude we will have after this inversion about mean operator. So inversion about mean operator, these two things are basically doing. So first mean is calculated and then inverted about this mean. So if you see after this inversion about mean operator, what is happening here? The amplitude of desired state, just a second. So amplitude of desired state is basically 5 by 2 root 8. And for other it was 1 by 2. So if you see here that after one iteration of Grover, amplitude of desired state is increased to 5 by 2 times and decrease for other by factor of 1 by 2. See here, originally it was 1 by root 8 for them. Now it become half. For desired state, it is 5 by 2 times. So basically, that is 2.5 times it has increased after one iteration. So since our capital N is 8 here, so we need to run it for one more round. Okay. So this was the initial state after one iteration of Grover. So all are having amplitude 1 by 2, and the desired state is having amplitude 5 by 2. Okay. Now again in the Grover operator, what we do is we change the sign of desired state, phase inversion. So what will happen? We will change the sign of this alpha 5. So some distortion is happening. What we can do? So idea is you understand this. Okay. Yeah. Can you give me 2 minutes to reset the slides?
Yes, sir.
Yeah.
We do understand, not an issue, sir.
Yeah. Okay. So what is happening here is that after the in the second iteration, we will change the sign of this. So basically it is minus alpha pi. So it will be below that. Okay.
Yes, sir.
But it is increased. Value is increased. Sign is changed. Okay. Now again we are applying that phase inversion operator. Will change the sign. And inversion about mean what will do? So again we have to compute the average. So now average will change. So now all the other states are having amplitude, that is 1 by 2 root 8. So 7 states are having this amplitude, and the desired state is having minus 5 by 2 root 8. So if we compute again the average, then it will be this 1 by 8 square root of 8. Okay. Now again we apply this inversion about mean operator. So that is basically minus v plus 2a, and v is the amplitude of the state. So for this non-desired state, we will put the value 1 by 2 root 8. Then this will be the amplitude. For desired state, it will be 11 by 4. So earlier it was 5 by 2. Now it has increased to 11 by 4. So if we compute this 11 by 4, then it is basically much more than the other states. Let's see how much it is. So after two iteration of this Grover operator, the amplitude of desired state is basically 11 by 4 square root of 8. Okay. And that turns out to be 0.97. And for other state, it is minus 0.08. So see the amplitude difference. Two iteration, it is having 0.97 amplitude, and the other are having 0.08. So what will be the probabilities of the desired state, mark state? Just need to square the amplitude. So that turns out to be 0.94 of getting the desired answer on measurement. And for other state, if you just square it, so squaring this term will be 1 by 28. So basically probability is further less, 0.007. Okay. So all other states are having this much probability, and it is desired state is having 94% probability. And as we yesterday seen that sum of probability should be 1. So desired state is having this much probability, and the all other are having this probability. So 7 times of other states. So it is pronounced to be 1 only. So what will happen after this second iteration? If we measure, then we will have this 101 state with probability almost 1. Practically, if we do 94% time, we will get this state. Okay. So when we get this state with 94% probability, then we can decide that this is our desired answer. So is it clear till now, or some doubt is there?
Sir, understood, sir.
Okay. So basically two things are happening. One is changing the phase, and other is increasing the amplitude of the desired state. And that we have to do how much time? Square root n times. So basically order of complexity is basically how much time you are applying this operator. So it's square root of capital N time. So complexity is basically governed by this square root of n term. And how this square root n is derived, that after this many iteration only we will have desired answer, not before or not after. So that proof I will show in the later slides, that from where this square root n came. So
Excuse me, sir.
Yeah, please.
So there's one doubt regarding the phase change of the required
state.
Phase change of the required thing that we are searching for. How are we doing that only for the required thing and not for others? Like how is that f of x determined? Will it change?
No. So just see. Okay. Keep this question in mind. When I will show demonstration, I will show you how it is changing.
Okay, sir. Yeah, thank you, sir.
So time being, you understand this algorithm work in this fashion, and now we want to see how this algorithm can be geometrically understood, or how this square root of n complexity came.
Okay, sir.
So what we are saying here is, if we represent the problem in this kind of geometrically, so what we are saying is, this is our state psi, which consists of desired and non-desired state. Okay. So here we are having all the state, and what we are saying is that out of this, alpha states are non-desired and beta are desired. Okay. Desired is basically x0 we are looking for. So what we are saying is that initially most of the states are non-desired, and out of them one is our desired state. So this vector will be close to non-desired state vector alpha. Okay. So what we are doing is, there are total 2 to the power n choices. Out of this, all x which are not equal to desired state are forming the non-desired vector alpha, and beta is our desired vector. Okay. And this alpha plus beta is basically this psi. So what is basically happening here in the algorithm is, so so can we write this psi as combination of this alpha and beta? Yes, we can write. This is simple vector kind of thing. So psi is a vector, so we can write it in terms of alpha and beta. And what is alpha and beta? Alpha is collection of non-desired state, and beta is collection of desired state. So we can write as a vector psi like this. Now what we are saying is, those two operators which we were using in the algorithm. So first operator is basically doing, it is inversion about what it is doing. So it is basically changing the phase. So whichever state is desired, so if we see it, and then it is doing the inversion about this alpha axis. So initially this state was having theta by 2 angle with this alpha axis. So after this inversion operator happens, this state psi is changed to this order of psi. So basically oracle operator we apply. So it turns out to be theta by 2 will be minus theta by 2. So we will come here, and then we apply the inversion about mean operator. What that will do, that will modify this order of psi state to this g psi. So after application of this Grover operator one time, our angle theta by 2 was there initially with this psi. It will change to plus theta angle is increased in the desired state. So we are here initially, one iteration of Grover will increase the angle by theta. So initially, like we can write the state as a cos theta by 2 plus sin theta by 2. Original state this. We can see, we have yesterday seen that we can write like this value also, and we can write this as a cos theta by 2 plus sin theta by 2. So if theta by 2 is the angle. So after this Grover iteration, what is happening is theta is increased. So vector psi is making angle theta by 2. So now it will make angle theta plus theta by 2. So what we are saying here is that one iteration will increase the angle by theta. So ultimately theta plus theta by 2 is basically 3 theta by 2 in one iteration. If we apply k such iteration, so basically our target is to reach here, or maybe more than this. So our target is to reach towards beta. So one iteration increase the angle by theta. So how many times we want to increase this angle so that we reach near the desired state? So let's suppose we do k iteration. Okay. So if we apply this operator k times, then increase in theta will be this 2k plus 1 by 2 theta. So basically one time if it is increasing theta, so k time it will increase angle k theta. So k theta we added to the original theta by 2. So this will be the expression. Okay. Now this is the thing which we are seeing here. So okay, so basically total size is n, and what we are saying is that let's suppose m is the solution. So generally solution states are 1. So m is 1 basically. 1 is our solution state and other are known solution. So first step I told that we are writing the state in terms of non-desired and desired state. Okay. So just what we are doing here is we are deriving the expression, complexity expression, that is basically pi by 4 square root of n. So how we come to that number that we are seeing here. So as we have explained here that one iteration increase the angle theta. So we want to increase k times such that this k theta is leading this psi towards b. So let's suppose if we assume that after k iteration, so initial state is this, one iteration increase theta. So k iteration, it will be this much. So let's suppose if we are saying that after k iteration, our this k theta is almost near to this axis, then we are done. So we want to determine the value of k, that how many times we should apply this k on this state psi so that we reach here. So what will happen if we reach here? Then probability of getting this desired state is high and probability of getting non-desired state is less. So see here. So this is the axis. So basically this is n by n minus m. So here if we put, yeah. So what we are doing is we are trying to calculate the value of theta by 2. Okay. So we can write like this. Sin theta by 2, what will be sin theta by 2? If you see here, this psi is, length is 1, and this is, so sin theta will be m by n, square root of m by n divided by 1. So sin theta by 2, and what we want here is this theta by 2 is generally towards this axis only. So theta by 2 is always very small and very less than this pi by 4. So when this theta by 2 is small, because initially this vector is towards this alpha axis, because almost all states are non-desired of consist of alpha, and there is only one or few states are of this. So this theta by 2 is initially very small and we want to increase it. So when theta is small, we can write this sin theta by 2 as theta by 2. So just some simplification we are using. When this theta is small, you can write theta by 2 is equal, sin theta is equal to theta. And that is basically sin theta by 2 was square root of m by n. Okay. So what we are saying here is in k iteration we increases the angle by k theta. That is clear. And what we want is k theta by 2 should be less than pi by 2. Why? So in k iteration we will be having this k theta increase in angle. So we want to just reach here, not cross this. So this k theta should be less than pi by 2, because this entire thing is pi by 2. So our k theta should be less than pi by 2. Okay. So now what we are doing here is we are just putting the value of theta from this equation. So what is the value of theta? Can anyone tell?
Theta is generally small, so we have removed a sign, but we want the angle should be less than pi by 2.
Yeah. So what is the value of theta? Can we see here from here? Theta by 2 is basically square root of m by n.
Yeah.
So I want to put value of theta here. So theta will be basically 2 times of square root of m by n.
Okay, sir.
So we put the value here. Okay. And that we want to approximately pi by 2. Okay.
Yes, sir.
Then we solve it. So that is basically pi by 4 square root of n by m. So the original expression is basically original number of rounds which we have to run is pi by 4 square root of n by m. Since m is generally 1, so we can discard that m also. And generally m is very, very less than n. So m can be, for simplicity, m can be removed. And this pi by 4 is some fixed constant. So in big O notation, we can write that it's order of square root n, not n. What it should be? It should be this pi by 4 is the square root of n. Because n is above, na? N is the total size. M is desired states. So desired state is generally one or few only. So that we can remove in big O notation. So when we calculate the complexity in or big O notation, we just keep the significant term, that is square root of n. So here square root of n. So here what we have seen is how to derive the expression square root of n complexity. So the exact complexity is of pi by 4 square root of n by m. Okay.
Yes, sir.
So now what we will do is we will do the circuit implementation and try to understand how this algorithm works on implementation. So if you see this algorithm, so here this all things are constant for all the algorithms. One thing which changes is Grover operator. In the Grover operator also, what changes? This fx changes. Other things are same for every algorithm or every kind of problem. Are you getting this problem? That
Yes, sir.
in this entire Grover operator and Grover algorithm, this fx is different. Okay. Sometimes that our fx is satisfying here this value 10. Okay. Sometime if we are looking for, let's suppose 11, then there will be some different fx. So what we have, whatever value we are looking for, we have to design this fx accordingly and implement that. In algorithm, every part is like kind of fixed only. Only this fx is changing on, that is also according to the searching problem which we are searching. Okay. So let's suppose our fx is like this. Fx is basically, let's suppose 2-bit function is there, and I am saying this fx is basically x1, x2 bar. Then it will satisfy 10 or 11.
Sir, X1?
No, what I'm saying is that let's suppose this fx is x1, x2 bar. 2-bit function is there, that
Okay,
is
sir.
x1 and x2 bar. So what is the
Either
satisfying assignment for it?
1 or 1 0 or 0 1?
No, not 0
Sir,
1. 1 0 only.
1 0.
Yeah, first
X1,
bit is
X2
x1.
bar. X1, okay, sir. 0.
Okay.
Yes, sir. X1, X2 bar.
Yes.
Yes, sir.
And let's suppose the function is x1, x2, then 1 will satisfy.
1 1. Yes, sir.
Okay. So what we are saying is that whatever the item you are searching, you have to design corresponding fx.
FX.
Okay.
Yes,
So
sir.
here, let's suppose if you are searching for this 1 then function should be such that on 1 it will satisfy the function. For other value, it will not satisfy. So let's suppose the simple function we have taken here, but in real problem, this fx can be any complex function which we want to search for.
Search for. Okay, sir.
Okay. Let's suppose this fx is 2-bit here. Let's suppose if you are having a complex function with n bit values and n bit value function is there. So if we want to find the satisfying assignment for that function, then what we have to do classically? We have to search for all possible 2 to power n assignment, and then we will be able to get the satisfiability. So the problem is that whenever whatever you want to search, you should have a corresponding function fx, and you should be able to implement that effects using quantum gates, and that too in reversible kind of thing that we will see in the implementation. So circuit we will see in the later session. Okay.
Okay, sir.
So now you understand what is the importance of this thing. So complexity we come to know that is basically square root of order of n. Okay. This pi by 4 and other thing we have discarded for simplicity in B1 notation. So it can be used for breaking the ciphers. Can it be used? So just update yourself that what we are saying here is that this Grover search can do searching for satisfiability also. Let's suppose some function f is there and you want to find one assignment that satisfy the function. So we can search that assignment also in order of square root n time. Okay. So we will see how we can do this thing. Satisfiability also we can do. Traveling salesman problem also we can speed up. Otherwise, in the worst case, we doing this thing in order of n time there. Using this, we can do it in order of square root n.
Okay.
So if you see here, then n and order, square root of n, you will say, okay, it's not that much, but it is pretty significant and substantial. Let's suppose if we go for searching a database of 1 billion records. Okay, let's see the Aadhaar record of our Indian UID. So there are, let's suppose, almost 1 billion plus entries are there. So suppose for simplicity, let's suppose there are 1 billion records. So that is basically 10 to power 9 records are there. So if we do classically searching for one record, then what will happen? Average complexity will be n by 2. Is it clear? Classically, if we do, then we have to search on an average n by 2 entries. So here n is 10 to power 9. So n by 2 is basically half billion. Assuming this data are not sorted, so best classical algorithm will do in half billion searches. Okay, half billion time on an average it will search the half database, then it will be able to search the item. But if we apply the Grover search, then what will be the complexity? Just do the square root of this term. So what will be the square root of 10 to power 9? Can anyone tell?
It's something given there, is it, sir?
No. Mathematically, this 10 to power 9 is the n. Then what will be the square root of 10 to power 9?
Square root.
Can anyone? So okay, let's tell square root of 10 square.
10, sir.
So how did you do that?
Simple.
So that's
10 power, same thing. It is 10 power 9 means it is somewhere 10 power 4.5.
Yes. That is I am asking. So
yes,
it will
sir.
be 10 to the power 4.5.
4.5.
So that number is this much.
Yeah.
So if you see, it is half billion. That is basically very much compared to this small number. That is 31,000 only.
Okay, sir.
So you can see that square root of n and order n, they are substantially high. If we increase this n, here this n was 1 billion, so we are seeing this kind of speed up. Okay, but if we increase the n to let's suppose 10 to power 50,
so it is 10 power 25.
So it will be 25 is very less compared to 10 to power 50.
50, yes, sir.
You should appreciate the difference.
Yes, sir.
But the condition is that we should have a quantum computer, and in that we should be able to represent this database. Then we can apply this search.
Okay.
So the other example is like in the cryptography also what we do is simply some plain text message is there, some key is there. So what we do, we just let's suppose XORing this, then we are getting this kind of cipher. So I think you must be aware about cryptography. So there is an algorithm called DES. So where this key size is 56 bit. Okay. So how many total possible keys will be there? 2 to the power 56.
Sir.
Okay. Yes, and that number turns out to be this much. 36 quadrillion.
Okay, sir.
2 to the power 56 by 2. Okay.
Yes, sir.
On an average, half we will take the space. And if we apply this Grover search for searching this kind of key, basically what we are trying is using DES. Let's suppose someone has used some 56-bit key, particular key they have used. And if we have that key, then we can decrypt the messages. So for that, but we don't know which key is used out of this 2 to the power 56. So what we are trying to do is we are trying to exhaustively try all possible keys. Okay. So if we try exhaustively and try to find matching ciphertext, then we have to do this much trials.
Okay,
If
sir.
we do the same on quantum computer using Grovers, then that will be only 1.18 millions only. That is a small number compared to this large number. So those kind of algorithm will not secure because 118 million is not a big number to current computer technologies. So here is the proof. I have proof or some kind of derivation I have proposed that how you can decrypt this DES kind of thing using these Grovers. So see here. So as I already told that DES is having key size of 56 bits. Is it clear?
Yes, sir.
So total keys are this much to the power 56. And what is the idea? If we want to do this thing on classical computer, then what we will be doing? So let's suppose this is the plain text P. Encryption algorithm is basically DES. So what we are doing is on this plain text, we are applying this encryption algorithm E using this key. Then we will getting ciphertext C. Okay. So the adversary don't know about this K, although he know this E, P, and C. Okay. So only the secrecy or the security lies with the key. So key is unknown. And what we want to do is we are having this EPC with us and we want to determine this key. So what can we do is we can try exhaustively all possible keys. And whenever we, let's suppose we apply one key, one possible choice, and on P, then we will getting some C. So whenever, let's suppose you are given some P and C pair, okay. For some plain text P1, we get some C1 pair, but key we don't know, okay. So what we will do is we will take this P1 and apply all possible keys and try to match with the given C1. So whenever this C and C1 matches, we say that, okay, we have found the correct key. But the problem is that this key size is enormous. That is 2 to the power 56. So average case 1 by 2. So this much keys we cannot try easily on a computer. But nowadays, this thing can be done on a supercomputer. But if we increase this kind of number to, let's suppose in AES, this number is 128. So those things you cannot do on even supercomputers also. So the this thing is taking this much time on a classical computer. But if we use this Grover's algorithm and how to design that F for this problem, that is the thing which I want to explain you. Okay. So what we are trying to do here is this K we don't know. Okay. So K, what we are doing, we will be implementing this K as a input data bits of 56 qubit, and we will create equal superposition of those 56 qubits, and that will represent this entire space of 2 to the power 56. Okay. So in the quantum computer, what will happen? It will have all possible keys here on equal superposition. And what we are saying here is that this function, this an algorithm is there. So what is unknown in this function? Only K is unknown. Okay. And what we are saying is whenever applying this Fk, if this is equal to this, then we will say it is satisfying. So for particular correct key, this EKP will equal to C. For other non-desired or non-correct key, it will not equal. So what we are saying is this Fk is a function of this kind where encryption algorithm E is given, P is given, C is given, and what we are doing is unknown is only K. So this function is in terms of K, and whenever this is equal to correct cipher, then it will equal to 1 because this operator equal is when it will equal when the correct key is applied. For other it will be Fk will be 0. So this is the function we have to implement in Grovers. Once we have implementation of this function, because it will depend on this encryption algorithm, so the steps will be implemented and k will be remain as a variable to this function. And what is the size of this k? 56. So k will consist of 56 qubits. Okay. So once we apply this Grover algorithm, we will find the satisfying assignment of this fk, and that will be our correct key. So that we can do in the square root of this n time, okay, on quantum computer using Grovers. So that is basically 2 to the power 28 in quantum scenario. Okay. So using Grovers, we can do the brute force attack. This attack is called basically brute force attack. Okay, where we try exhaustively all possible keys. So using the Grover search, this exhaustive trial is speed up, and the complexity is drastically reduced from order n to square root of order n. And so basically the idea is that complexity is reduced from 2 to the power n to 2 to the power n by 2. What is that? Square root n?
2 per 28.
28. So basically by 2, 56 by 2. Square root, if we take.
Yes, sir. 28, sir.
Yeah. So this way I am done with the theoretical presentation. Now we will move to practical demonstration of this Grovers on a quantum simulator. So how much time we are left with? 15 minutes, 15-20 minutes are there. So we will see how we implement and how we can run this algorithm.
Sir,
Yeah, please.
and Grover's, what is their C?
What is?
C.
Tell me in the slide where that is the C.
Yes, sir.
Where?
E is equal, EKP is equals to C. So C
is ciphertext.
is what over there?
It is ciphertext.
What is that, sir?
Let's suppose you are having some message P, okay, in plain text, and I am applying some encryption. So I will convert it into some ciphertext, and if you send that message ciphertext, so only the person who is having this key K can decrypt it to plain text. For other, it will be gibberish. Means some random thing will be there, 64-bit. So other cannot understand. Only the recipient, the desired recipient who is having this key K can decrypt this and can get the original plain text message.
Is he the receiver?
No. Let's suppose I am sending some secret message to you. So let's suppose my secret message is that we will launch this mission on this date. Okay. So this is my plain text message. Okay. And suppose I am having some 56 random bit key. That is 10111, some 56 bit key is with me.
Okay.
And you're also having the same key. Okay.
Okay, sir.
So instead of sending that message, plain text message that we will launch this mission on this date, what I will send is I will apply this algorithm DES, that is encryption algorithm DES. So there are many algorithms. Suppose if we apply this DES, then this message using this key and this plain text, it will convert to some ciphertext. That is
okay, I got it now. It's a some text which is going to be sent. Yes,
it is
sir.
unreadable.
Yes,
So
okay, sir.
It will not make sense to anyone. Like if you get this something, then you will not try to make out any message out of it until and unless you have this key, and then you apply the reverse procedure. So basically, the reverse procedure is called decryption. So if you do decryption on this C using this K, then you will get P. So inverse is possible from C to P if you have this key.
Okay,
as
sir.
our understanding is there that you are also having the same key with you, so you can get this P, the secret message. For others, need to have this key. If they don't have this key, then what they can do is they can try all possible keys, but that exhaustive trial is not possible due to computational power limitation. Is it clear? Now so now what I'm doing is I'm demonstrating that Grover's algorithm on a quantum simulator, namely this QKit. So you can search it on Google, QKit is available freely. And once you download it, you can see this kind of interface is there. Okay. So there are lots of options are there that we will discuss. Okay. So you can load circuits from a file. Okay. So I have created some functions already implemented for you. So what I will be doing is I will just loading that file, circuit file. Okay. So you can also create your own circuit using this. Quantum gates are available, qubits are available. This bit you can add qubits using this, you can add gates using this, and you can run the circuit using this symbol. So you can also create this kind of circuit. So I have created already because we are running out of time. So we should use this circuit. And what I'm saying here is that I have implemented Grover search for function for value of 101. Okay, so this function, this Grover search will search for 101. Okay, so the function corresponding to 101 will be x1, x2 bar, and x3. 3 bits are there, and the function will be such that x1, x2 bar, and x3. So what will be the satisfying sample for this function? The function is x1, x2 bar,
x3.
x3. So for x1 it should be 1, for x2 it should be 0.
101.
101, correct? So our problem is that let's suppose but the item we are searching is 101. We have created the equivalent function, and the function we have to implement here in Oracle. Okay, or that in phase inversion operator, that we will see how we have implemented the function. Okay, so as in the algorithm explanation, 3 qubits are required for 3-bit Boolean function, and the 4th qubit is auxiliary one, that is started with 1 value. So initially this all 3 are in 0 state, and this is also in 0 state, the helping qubit or the auxiliary qubit. Then we apply this SX. Basically it is doing the NOT thing here. So here we will have 1. Okay, so simultaneously if you see this algorithm also, then it will be clear to you. So this step we are here. So all bits are initialized with 0 and 1 bit is initialized with 1. Okay, see here. So is it visible? This diagram is visible?
Yes, sir.
Okay, so the first step is done. So here we are. Then we have to apply Hadamard, and here also Hadamard. Okay, this is done.
Okay.
Now what we have to do is we have to implement the FX. And here our FX is simple, but in real life application, this FX will be very complicated and it is challenging to implement it. But here the FX is basically x1, x2 bar, and x3. Okay, so x1 value is coming here. Okay, and x2 is coming here. So what we require in our implementation?
x2 bar. Okay.
So we just apply the NOT gate.
Not.
It will become x2 bar. Here it is x3.
x3.
And what we do is 3 control Toffoli we are having.
Toffoli.
Okay, but in Toffoli only 2 controls were there. We have a gate which is having 3 control. So what it will do is x1, x2 bar, and x3 XOR with this 4 qubit. Is it clear?
Yes, sir.
Okay.
So here what we'll have, we will be having this function in this line. Okay. So if you are
fourth one,
we will be having this FX implemented here.
Okay.
So
the fourth line.
So the 3 is a control now, and this control will implement in this function x1, x2 bar, and x3, and that is our FX. Our FX is what? That is being XORed with this 4th qubit. Just see here.
Means 1, 0, and 1. So we are applying Toffoli at 101.
Not 101. You are having
no, I mean to say,
yeah, you are having all possible states here. Okay. all possible states with 3 qubits. But whatever these values are here, and we want to implement, just the algorithm part is there, that we should have this fx XORed with here. So if you see here, fx is coming here, okay, and here what we are having, 0 minus 1 by root 2. When we apply Hadamard on this state, it will become 0 minus 1. Okay? Is it clear?
Yes, sir.
0 minus 1, that is XORed with this fx. If you see, this qubit is XORed with fx only. These 3 qubits are ended and they are XORed with this 4th qubit. So what is happening here is that these 3 qubits are giving an impression of fx here. In this way, using this stuff only, we have implemented fx and we have XORed this fx with this qubit. Okay. So now fx has come here, and what we are saying is that is XORed with 0 minus 1. So whenever, so all possible values are here, and whenever these values are 101, then what will be the fx here? The fx will be plus 1 there, that case. Or other cases, what will be the fx? It will be 0.
Minus.
So
0 minus 1.
So what I'm saying here is, these 3 qubit are having values x1, x2 bar and x3, and that is being XORed with this 4th qubit. And this f1, x1, x2 bar, x3 is our f, and we are XORing with this 4th qubit. And here also you see, when we when this fx is 1, so because this fx is having all possible input x values. So when we apply 0, 0, 0, this fx will be 0.
0.
Okay, so it will not make any effect on this 4th qubit. It will make effect on this 4th qubit when only this is 101. So when it is 101, these 3 qubits are 101, then only it will be 1, and then it will change the sign of this state. So 0 minus 1 is XORed with plus 1. So XORing with 1 will change the value 0 minus 1 to 1 minus 0. Understand here? Here we are having 0 minus 1 state, and that we are XORing with plus 1 state. So XORing with 1 will change from 0 to 1 and 1 to 0.
1 to
so
0.
this 0 minus 1 will become, so see here, here is 0 minus
1 minus 0.
1 minus 0. So we can take minus out of it. Then it will be again minus sign of 0 minus 1. Okay. So this way we have derived this minus here that we were explaining now.
Okay.
So see here, the desired state sign will change. Okay.
Yes, sir.
When it will be minus, when this value are 101, then only it will become 1 fx, and then it will change the sign of, in that case, whenever this is 101, then only it will change the sign. That is the thing we were trying to do in our algorithm. So for 101 case, because all states are there available with us, when we apply, when internally our 000 is applied, this fx is 0. When 110 is applied, it is 0. So all states, it will not make any effect. Only when this fx is desired state, that is 101, then only it will 1, and then it will change the sign. So that was our requirement. If you see here, for whenever fx is 1, then only sign will change. Otherwise, it will not change the sign. So this is the oracle operator. Here what we are doing is just again, because we changed this x2, so again we have to restore it to original state. Okay. So we just nullify the effect of this x gate here. Now comes our amplitude increase operator. So what we'll be doing here is, as you have already
This
seen
is
in the diagram,
XOR.
see here, you have to apply Hadamard. Okay, this is kind of fixed kind of thing. Okay, and to implement this, you have to use, see here, this control Z will do the control Z will do the thing to implement.
Now this is opposite XOR X and XOR.
So this is the part of algorithm Hadamard, and here this operator, this circuit will do what it will do is, this part will change the sign of all state except 0, 0, 0.
Okay.
So first component just change the sign, second component has change all the states except this, and combined effect of this Grover operator, these two things. After this, here, what will happen? Here initially all are having equal amplitude. After this, amplitude of desired will increase. Okay.
Yes, sir.
Is it clear?
Yes,
So
sir.
here, if you see, here we try to implement that oracle operator. That is basically it will do the change the sign of desired state. And here what we are doing is that inversion about mean operator. This head-amad were extended part of that. And this small circuit is doing the changing the sign of all state except 0, 0. See here, head-amad, and this is internal thing was doing this thing. Okay.
0, 0, x minus x for x is
So it changes the
greater
sign
than.
of every. Okay.
Hmm.
So let's quickly run this circuit and see how it is progressing. So what, see, as it is a 3-qubit case, so capital N is 8. So what we have to do is we have to run it 2 times. So the same thing is implemented 2 times. So here, if you see this circuit, so again we are implementing this again. Okay. See here, these 2 things. Okay. So the same thing is replicated again. Okay. For 2 iteration. Okay. And then finally we are going to measure. Okay, so let's run this circuit and see the step-by-step evaluation of the states. So we have run it. So once you run, then this state vectors comes here. Okay. So if you see here, all the states are available with this 4 qubit because this fourth is also considered here. So due to this 0, -1, alternate states are having negative. So just see here, this red is showing the negative amplitude and it is showing the positive one. Okay. And here this is the first qubit, second qubit, third qubit, and fourth qubit. So first one is above, second, third, fourth is like this. We have to read. So initially what we are having is all the state are in equal superposition, this 4 qubit, and since it was not 0, it was 1, so we are having this negative amplitude here. Okay. Then what we are doing is we are applying this operator, and what it will do is it will change the sign of desired state. So where is our desired state in this?
101.
101. So okay, just a second. So where is 101? So if you see here, it is 101 here, 101 is here, 101 is here, and where else? Nowhere else. So these 2 states are having our first 3 qubits as 101. Here,
Last 3 also.
where?
No, it is not 101. Only these
So
two,
yeah,
sir.
starting from the top. This is the first qubit, second qubit, and third qubit. So top 3 qubits I want 101. So
Okay.
they are here only at this stage. Okay. So what should happen?
11 and 12.
Yeah. So if so what will happen is amplitude of this state will change. Okay. If it was red, then it will change to this, and if it was this, then it will change. So see here. Okay.
Yes, sir.
Let's see here. Okay. After this, see, due to that changing, we are having this.
Okay.
Okay.
Yes, sir.
Yes, sir.
Got it.
So this step is done. Now the second operator, what it will do is, okay, just let's with us. Okay. Now what we are saying is, after this operator implementation, what should happen? The amplitude of desired state should increase and other should decrease. So what when it will happen? See here. Okay. So this is till now we have done the one of Grover operator. So if you see here, see the desired states are 101. So this is happening here and here, and their amplitude has increased. Okay.
Yes, sir.
Is it? Okay. And other
Yes,
states
sir.
is decrease. So probability will also increase. Okay. Just need to square them. Okay. So same thing if we apply 2 times, then what will happen? It will further increase.
Amplitude increases.
Further. Okay. So where we will see this thing. Okay. See here. Here, the last step we should see. See here. The desired state is having 101 and it is having the highest amplitude. So
why not for the other one, sir? Oh, okay. So this
no,
bit,
this
fourth
is
bit.
this
Yes,
is the
sir.
thing which you want to do, no? This
Yes,
is the item we are searching for.
Adam,
yes, sir. Okay, I thought even for this it will increase, but since it is 0, okay, sir.
sir,
But here, if we not apply
when
the
we
header mart,
use,
yeah,
sorry,
yeah,
when we
please.
use header mart, so here we are using in the middle two header marts in the same way. And we are
Where?
looking over there that there are two negative. That means it is changing their face, isn't it, sir?
Where exactly? Can you tell me? Here?
In middle, that state, middle one. So
Where?
here,
Here?
no, middle one.
After
Two
one
header
iteration?
mart, two header mart. We apply over there, left and right.
Okay, just let
Left
me.
of CZ and right of CZ. There we using the two header mart over there,
Left of CZ here.
and right of CZ. There also we are using the header mart.
Yes, yes. So if you see the algorithm part, then it is there. This header
Yes,
mart and
sir.
header mart are left and right side part we are doing. So
Yes, sir.
ultimately, this implementation is giving that overall picture that it will finally, this grower operator will increase the amplitude of desired. So if we apply 2 times, then it will be significant. And also we can verify the same thing that like here, if you see.
So could you
Okay,
please
so at
show
last,
the result of left one and right one also? These states.
where? Here?
The header mart used over there, that is state, left side of the CZ.
Left
Yeah,
side of this CZ here.
here. Yeah,
Yes.
here. Yeah.
So here will be here will be some you can say some changes are happening, but you have to see the operator in combined form. So this total application of this gate will give that thing. Here the states are moving left right. So if you see here the presentation also, what is happening is in between. If you see then phase once we change the phase of desired state after this header mart, what is happening? Sign changed happen between
Yes,
these two.
sir. As the
Here, if you see the sign is
hazard
changing
change
here.
its face, so whatever the
Yeah.
direction, it will oppose the direction. So when we are using the another hazard over there, so it should oppose it back. Suppose it is going in 180 degrees, so it will go back to the 360 in the same
Yes.
direction, isn't it, sir?
Yes, yes. So basically, this header mart is causing this constructive and destructive interference in this thing. And
So
this
could you
CZ
please
is
show the other hazard's result also
where?
at the right side of
Here?
CZ?
Right side of here?
CZ. Yes,
Before?
sir. Yes, sir. Before and after both, sir.
Okay. Yes, that is before.
Okay, now I understood, sir. So at the there it increases the amplitude at 111, and here it increases the amplitude at 000.
Yeah. So you have to holistically understand this thing that this entire, if you see this part, so this part is not this part. This part is your oracle thing. Phase inversion
Yes,
thing is
sir.
going here, and
Yes,
this is
sir.
your this complete thing is your inversion about mean operator,
Mean
and
operator. Okay.
in that also this internal part is the phase changing every state except 00.
Okay, sir.
So
Okay, got
here,
it, sir.
so here if you see, we have seen the amplitude. If we see the text data, that what is the probability and amplitudes of this, then we can see here. This is the amplitude of the desired state. So from left 101. So what is the amplitude? 0.9722.
9722. Okay, sir.
And it is the amplitude. So if we see our example, see here. After 2 iteration, this was the amplitude of desired state. And what was for the other states? That was minus 0.08. So if you see here, for other state, it is minus 0.088. Okay. So the same
Yes,
thing
sir.
is happening here for desired state this much. And when we see the probability amplitude, okay, so we can also see the probability amplitude of the final state. Okay. So this thing is the amplitude, this thing is the text value of that amplitude, and this is the distribution. So in the probability case, what is we are going to do is just mod square the amplitudes. So we will have
101.
this much with 94% probability, we will get this state. So since because for so why we are getting this?
It is refining the result now.
Yes. So because basically we are doing this kind of thing in simulator. If we do this thing on actual device, then some variation also happen. That some will occur with more probability, some with less probability. But the overall idea is that more than 50% probability, you will get your correct answer. Is it
Okay,
clear?
sir. Yes, sir.
So I think I am done now. If you have any question, query, then please ask.
Sir, did you perform any practical on this, whatever you showed on simulation?
Yes, that we are not authorized to discuss on this kind of platform.
Oh, okay, sir. Okay, sir.
Sir, if n is equal to 2, I think with one iteration, I'll be able to
It will
get
do.
the maximum. Is that not, sir?
Yes, yes.
Yeah, thank you, sir.
Okay, yeah. But the exact iteration number is pi by 4 square root of n by n. If you precisely, because what is happening here is that in case of 8, what is happening? So the number should be pi by 4 square root of 8 by 1.
1.
This number of iteration you should run. But that number
Okay,
is
sir.
not turning out to be an integer.
Okay, sir.
If that turn out to be a perfect integer, then we will get with more than 90 or 100% probability also we can get the correct answer.
Okay, sir.
Yeah.
So as we increase the bit, it decreases the probability, means it divided equally in all. Like we are taking 3, for it will divide in all 8 parts. If we are taking 4, then it will divide it in all 16 parts.
Yes. So I'm not getting your question.
It means no. I wanted to know that I want to know the actual application of this. What I understood is that as we are increasing the efficiency, and we can reduce the time, means we can speed up the
Yes, yes.
data.
So
Is that so,
basically,
sir?
no. Just I think I should just again tell you the thing. See here. So basically what we are doing here is we are speeding the searching in general search column. So whatever search you are doing on classical, that was taking order and time. But that we can speed up using these grovers. So if you see here, in for 3 qubit case, capital N is equal to 8, we do only 2 iteration. If classically you do, then you have to run this searching 8 times. But
Yes, sir.
using this algorithm on a quantum simulator or computer, we need to run only 2 times. Okay, so let's suppose if we increase this n to capital N to 32, then you need to run only 5 times.
5 times. Okay,
and you will
got
get
it.
correct answer. But classically, if you
Right.
do, so this search is
We
having
need
wide.
32 times.
Yes. So this search is a very
Okay.
important problem, and it is having varied application in different domains. So as
So
we
this
also
is really
discussed,
amazing.
yes, yes. So
It
see here,
reducing time as well.
yes. So see here also we see this if can yeah I think it was clear in that 1 billion record kind of thing scenario. See here.
Again, I missed your all these PPTs, your
No problem.
presentation of the
Yeah.
starting, sir.
So see here, 10 to power 9 database is there. Okay, if you do search, then 500 million iteration you have to do for searching on classical.
Okay.
But on using rovers, only 31,000.
Okay.
So it is drastically less than the classical one. And it has wide impact on cryptography also and other thing also.
Sir, are we going to have this cryptography session in the afternoon, sir?
Yes, yes.
Implementation? Okay, sir. Thank you.
Yes.
Okay. Thank you, sir. You're very kind, sir. Thank you.
Okay, thank you.
Thank you.
Dr. Sunita, I am done.
Sir,
Dr. Yeah.
thank you, sir.
Okay.
Dear participants, do you have any queries? Then you can ask. Already, I think already all of you have asked mostly.
Okay, then
Yes, sir.
let's stop here. Okay.
Yes, sir. Thank you, sir. Again, we'll meet at 12 o'clock.
Okay.
Thank you, sir. Dear participants, we'll meet again at 12 noon. For now, I am going to end the session. Thank you all.